So this will be the first video out of two for looking at problems in section 2.5. And we've been building all semester to these types of problems. They're called optimization problems. And those are essentially figuring out maximums, minimums, right? Where we want to minimize cost, maximize profit, or we look at how much drug will give us an optimal performance. So it was the studies of trying to figure these things out that much of calculus came from. So this is the driving force for what we've been talking about. And some key things to keep in mind when we're looking at these problems. It's just like any other word problem. First, we have to figure out what we're trying to optimize. What is it that we're looking for? In this case, we're talking about the output, right? So that's going to be important. What is it that we want to maximize or minimize? So what we want to maximize or minimize. That's what we're looking for here. What is being optimized? And then the other thing is, what are the inputs, right? So the first step is always figure out the outputs and the inputs, just like we've been doing when we were doing the derivatives to begin with, right? Remember the units for them. Step 2, we're going to sketch and label diagrams if possible, especially if it's a geometric problem. We can use that to help us out. Step 3, construct a model with a single input variable. This is going to be very important for us because a lot of the things we're going to deal with have more than one variable. Think about, let's see, in geometric, like if we were talking about a rectangle, length and width, we're not going to want both L's and W's. We're not going to want two variables. We're only going to want one. All the derivative rules we've talked about so far only have dealt with one variable, right? What's the derivative with respect to x? Those kinds of things. So what that means is probably going to have more than one equation floating around in the problem. So we'll see which ones we can deal with. And then step 4, we're going to locate the optimal point. This is where we do our first or second derivative test. So step 4 is where we actually do the things we were doing in the last section. And when we do this, we're going to find the critical points. Right? So we're going to find the critical points. And then if there's only one, so if there's only one CP, we're going to use the second derivative test mostly. Right, we'll just put usually. So if there's only one critical point, we're going to use a second derivative test. And that, again, depends on the problem. If the second derivative looks really difficult to take, we might just make that sign chart we do for the first derivative. So let's look at an example to get started here. So I'm going to make this a little bigger here. If you have 100 feet of fencing and want to enclose a rectangular area up against a long straight wall, what is the largest area you can enclose? Okay. So what is it that we're trying to optimize? It looks like largest area. So this is what we want to optimize. We want to optimize the area. So he's going to be what I'm looking for. What else do I know? That I have 100 feet of, 100 feet of fencing, that's the total amount of fencing, right? Going to put that down. So that's the total amount of fencing, and it's a rectangular area. So let's draw what's going on here first. So I'm going to think about what's going on. So on this one side I have a wall, and then I'm going to have a rectangular shape, and it told me that, right, we have that if I have a rectangular shape, we're going to call these both sides x, right, because one's x, then the other one across from it is, and then this one we'll have to call y, because it didn't say square. So now all the sides have to be the same. And think about what you need to optimize. You need to optimize the area. So the area would equal x times y. But here what we notice is that we need only one variable. And the trouble is I got two of them. So we think about, well, what's the other things that relates x's and y's? So look at the other stuff we have in the problem. So this is where that step 3 becomes pretty important. We want just one variable. Let's see. The other thing that I know is that the total amount of fencing was 100 feet. So let's think about what that might look like. So over here, we only have 100 feet total. Right, so this is our total fence. And what does that have to mean about, what does that have to fence in? So if we're going to use all the fence, it'd be for the two sides that are x and the one side that's y. We don't have to worry about the wall side. So that means 100 is equal to 2x plus y. So now what I can do is I'm going to solve this guy for y. So y equals 100 minus 2x. And I can take this 100 minus 2x and plug it in over here. And if I do that, I'll get rid of all the y's. So let's go ahead and write that out. So the area would equal x times 100 minus 2x, which is 100x minus 4, or minus 2x squared, isn't it? So there's my area with one variable. What do I got to do now? I got to maximize or minimize this thing. So let's do that. So I'm going to move this over just a little. So we're going to find the critical points. All right, so find critical points. Our original function a is 100x minus 2x squared. So the derivative, a prime, would be what? 100 minus 4x. Critical points say I set that equal to 0. So let's solve that. 4x equals 100. So x is 25. So there's my critical point, x being 25. Now what? Well, we can see our first derivative was the 100 minus 4x. Pretty easy to find the second derivative. So I'm going to use that test to figure this guy out. So second derivative test. All right, so second derivative, a double prime of x. He would be what? Looks like he would just be minus 4. Minus 4. But remember that means rewrite that guy. So now we know it's a maximum. But be careful, back in the original problem it asked what was the largest area. So I don't want to know what x is, I want to know what a is. So back over here what I would do is say, okay, well then what's the area at 25? It'd be 100 times 25 minus 2 times 25 squared. So a at 25 is, when I got it, I had 1,250, and that would be in what, square feet? Is the max area. So there's my maximum area. Now be careful, because so this is the answer to the problem. So we're done. A variation on this kind of problem would be, well, what are the dimensions? Come back over here, the dimensions. That means what were x and y? What were those guys? So we know what x is. X is 25. So let's pull this down here. So what about the dimensions? Well, we know x is 25 feet. And we know y is 100 minus 2 times the x. That's 100 times 25. That means that y was... So when we think about it, the area is 25 feet by 50 feet. Okay. Now we weren't asked that in this problem, but that is a variation on this type of problem. So just be careful, make sure you answered what the question asked, and also make sure your answer makes sense. If this had been a negative number in terms of the area, something went wrong with a sign somewhere. And remember, most of the time where the error happens is not necessarily the calculus step, but one of the 14 steps of algebra that we have to do. So just be careful. So this will be our first video for section 2.5. The next video we'll look at example number 2.